All right, so we're taking a look at moments and centers. And so they're related to each other. So we started off with the simple idea yesterday of having some masses. If one's bigger than the other, then the center of mass is not going to be exactly in the middle. Okay? It's going to be closer to the bigger one so that we can balance. And these are called moments because the moment you move one of these, it's going to tilt. That's the best explanation I have for that word. So we then jumped into 2D moments. And we did a brief example of that. And by the way, what is a moment, really? What did I say, calculation-wise it is? Two-word phrase.
Weighted average.
Weighted average, just a weighted average, okay? Yeah, it's just weighted by where they are and how much they weigh. Okay. So if we go two-dimensionally, so let's say we have this rectangular plate, and we throw a coordinate system in there, we call that x and we call that y. And then we put some point masses on here. I'm not tracking right. So each one of these has an x and y coordinate and has a certain weight. And the weight's based on the center of the object. Then if I want to find the center of mass here, all I would have to do is a weighted average for the x values in the masses and the y values in the masses. So x bar is called the center x value. And what you have to do is then find each x value, let's call them xi, find the mass associated with that x value, right? And then add those suckers up. That's the weighted average or the weighted sum part. To make it an average, you have to divide by the total mass.
The same Cartesian coordinate?
Mm-hmm.
Why are they reversed? Some y.
What's reversed?
X on the y and y is on the x.
And this is an x here, up to y there.
It's the lines in the middle.
So the axes, this is the y-axis, and that's the x-axis. Yeah, no, I put them on a rectangular square plate. So I'm putting them on a square plate, and I'm putting an axis in the middle of that square plate. Okay. And similarly, the average y value is just going to be the sum of each y times its mass. That's the weighted sum part, divided by the sum of all the masses. And we did a quick example of that last class. Now, to connect the centers to the idea of a moment, okay? So if I move one of those and I know the balance and I have the balance point, then either I have to move the balance point or the whole plate's going to shift the moment I move something. Right? So that's kind of the idea of a moment. If I move something like in a certain direction, like in the y direction, that means it's going to spin around the x-axis. Right? So if I'm talking about a moment with respect to the x-axis, that means I'm concerned about the distance of an object to the x-axis. Object to the x-axis. Object to the x-axis. Object to the x-axis. Okay. Right? Now, the distance to the x-axis is a y value. With me?
Yes.
Okay. So this particular sum right here in the numerator, that sum is called the moment about the x-axis. Because the y value measures the distance to the x-axis. That's what this sum up here in the numerator is going to represent. That's the moment about the y-axis. And that always threw me, but the bottom line is when you find the average x value, you do the weighted sum of the x's. When you want the weighted sum of the y values, you find the weighted sum of the y's. But the numerator of each of those has twisted names just because of the way things turn physically. Okay. So just something important that we need to know. So now, this is if I have discrete points going on, instead of a continuous flow of material. Okay. So So that's when we have to get into calculus. That's where we're going to move to next. So now we've got moments and centers with calculus. So the main thing we're concerned about here is the idea of finding the center of mass of a two-dimensional object. And the two-dimensional objects we're going to work with here are we have some single function f of x, we have some value a, we have some other value b. So we have this just thin plate of material. Now, although you could have a density function sitting in here too, determining the mass at each point, we're not going to get to that because that's going to involve double integrals. Take Calc 4 or 5 for that. So I want to figure out where, if I have uniform density, so that's another catch here, we're doing uniform density. Okay. What's the mass of this, and then what's the center of mass of this? Well, the total mass is pretty straightforward. If it's uniform density, all I need to know is the area and the density value per unit area. So rho is what we use for that. So the mass of this plate will just be its density value times the area. That's pretty straightforward. How dense is it? It's rho dense. How much area do you have? There's the area. So there's the total mass of it. Sometimes these plates here are called lamina. They're just thin sheets of stuff with uniform density. All right, so next thing we need to do is figure out how to take that and turn it into a center of mass. So to do that, I'm just going to isolate a rectangle in here, like we've done before, to get area. And I'm going to use that area rectangle to help me figure out the center of mass. So if you think back to when we first developed integrals, we picked some special x value inside of that interval, and we called it x star. Remember? X star is some x value inside this interval. Maybe that x value right there. Could be any one inside. It could be the left endpoint, it could be the right endpoint, it could be the midpoint. For this example, since I'm looking for a center of mass, I want the midpoint. Okay. So in this case, x star is the midpoint of the interval. So that gives me the middle of x value in this rectangle. And rectangles are nice to work with because they're rectangles. Okay. The middle y value, that should be pretty easy to get. I take my x star, I plug it into my function. The y value is f of x star. What's the middle y value then? Just half of it, right? Take that y value and divide by 2. So to get the midpoint of this rectangle right here, I'm just going to say, hey, x star is the midpoint. And then the mid y point in there is just going to be f of x star over 2. That's the mid y. All right, so next we need to generate the moments, and from the moments we'll generate the centers. So if I want to find the moments about the x-axis, so to do that, imagine that we spin about the x-axis. I need to get to that center point. What gets me to that center point?
Y.
Over 2.
Yes.
Yeah, so y over 2 gets me there. So I'm going to have a y over 2 is going to be the value I want. And the moment, remember, is a weighted sum. What's it weighted by? Well, in this case, it's weighted by the area of the rectangle times its density. Okay. So the weight of that y value is going to be rho times the area of that rectangle. How do I find the area of that rectangle? Base times height. My base is delta x. My height is f of x. Or just call it y here for simplicity.
So y is just a function.
Yeah, y is just a function of x. I'm just going to call it y for simplicity here. Sorry that my pen is not tracking right. I'm going to have to switch to the other tablet thingy. Now, that's just one rectangle. If I want all of these rectangles, I've got to integrate. Yeah, I've got to integrate that.
Where did
So-
we get delta x from?
Delta x is the width of the rectangle,
Okay.
which when I take this to the limit and turn it into the integral, it turns into a dx.
Okay.
Okay, so if I put all of that together, so this is just one of those moments. I gotta add all the moments up. So to get the complete moment, I'm gonna integrate from A to B all of this stuff. So let's see, what do I have here? I'm gonna reorder it. The delta x turns into a dx. I'm gonna put that at the end. Rho is some constant, so I can pull that out. Because we gotta do constant density here for now. It's too complicated to do variable density at the moment. And then otherwise, I have a y times y, and I have a divide by 2. So I could pull the divide by 2 out, and then I get a y squared in here.
That's it.
But
So
you have
that's-
it with a dx. But you have a y and a dx.
Y is a function of x here.
Once we have
Nope,
it,
you still lost me.
once we have the function, you'll be able to replace that for y.
Yeah,
So
y
You'll have x.
represents my function of x.
Oh,
Sorry
okay.
about that.
I'm back.
Yeah.
I'm back in.
So that's the moment about the x-axis. The moment about the y-axis is pretty similar. There we go. Moment about the y-axis is going to look similar. So slight differences though. I'm going about the y-axis here. So that means I need to get from the y-axis to that rectangle, in which case it's x away. Okay. And then otherwise, I need to know the area and density of that rectangle, which is basically that mass function up there. Okay. So when I put that together, instead of multiplying a y by a y, I get x times y, right? X, and then the y comes from the area. So I need a new page for that. So just a little bitty one. I'm going to have the distance away, that's just an x value from the y-axis, times the density, oops, that did not come up very good, rho, again, not bad, times the area of the rectangle, which is y times x. And when we add all of those up, we get a complete picture. What's constant here?
Rho.
Rho is the only constant. The delta x turns into a dx, and otherwise I have x times y, and remember y is a function of x in this case. So those are the moments. Then I use the moments to calculate the midpoints. Now remember back here, the moment about y uses x's, and the moment about x uses y's. So I'm going to write this down in 2 different ways. The second way is more useful. First way is kind of technical. New page. So the average x value of a continuous region then is just the moment about the y-axis divided by the total mass. What's the moment about the y-axis? Well, the moment about the y-axis is just x times y prime. Let's see that. I think that doesn't sound right. Double check my notes here.
X squared.
Yeah, no, that's right. So up here, then I would have the integral from a to b of x times f of x dx divided by the mass, which is rho times the integral from a to b of the area, integral of f of x dx. And similarly, the center y value is going to be the moment about x-axis divided by the mass, which is the integral from a to b. Instead of x times y, we get y times y, or f of x squared dx divided by the mass, which is rho times the area.
Don't we have a bunch of constants though with
Oh yeah, this
The
one
moment of x.
has, yep, this one has a rho, and this one has a rho over 2. Thank you. Forgot this.
But doesn't something wrong on the bottom?
Yeah, we can clean it up, but usually we calculate each of these separately. Yeah, you can't calculate 2 integrals at once, so although, yeah, you could say the rows cancel out, we're going to just leave it in there like that. So if I make those integral calculations, so basically I have 3 integrals to calculate. I have the integral of f of x to calculate, multiplied by rho. I have the integral of x times f of x to calculate, multiplied by rho. And I have the integral of f squared to calculate, multiplied by rho over 2. Once I get those 3 numbers, I can combine them, and then they give me the center x value of that particular object. So let's try on a relatively simple object. Now, oh, who cares? Okay, well, a couple things we care about. So anytime you're building something, balance is an issue. Where is the weight distributed? Calculus can help us figure that out. Another thing that's kind of cool, remember we did some 3-dimensional shapes before? Rotating about axes? So there's a thing called the Theorem of Pappus. And what the Theorem of Pappus says is if you have a line that you're rotating something about to generate a 3-dimensional object, like a donut, but it could, donut, there we go. But it could be any kind of shape like that. If the cross-section of that thing is uniform through the revolution, and it has uniform density in one of those cross-sections, then if you know the area of that cross-section, and you know its center of mass, then all you have to do is follow the path of that center of mass. So that center of mass is going to make a path as I revolve, right? That path is going to be a circle, right? Because I'm doing a revolving about an axis. So let's say the distance from the axis to that point right there, let's call it r for a second. Then the volume here is just the area of that cross section times the path the center made, which is just 2 pi r. So it breaks down rotational problems that we were playing with into find the area of the cross section, find the center of mass, and then make a circumference out of that center of mass. Does that make our life any easier? Sometimes. because I still have to find that center, and finding that center means I have to use one of those formulas. Okay. So no matter what, I have to integrate it. This integral could be easier than the integral generated by disks or shells. Okay. All right, so now we have a third tool to generate stuff. All right, so here's the region we are going to play with. See if we can find the center of mass using those formulas. Let's make a triangle that is 5 tall and 7 long, and let's make it a right triangle. So I've got this area in here. I want to know where the center is. So there's some center in there. Where is it? Is it closer to that corner, or that corner, or that corner? Is it somehow in the middle if I were to just cut those two line segments in half? Well, we can find this. First thing to find this, I need a function for that blue line segment. What function is that? What's the slope there? Negative 5/7 x plus 5. Okay, so this is my f of x here. So things I need to calculate, and let's let rho be 1. So density here is 1. For simplicity, I need the area of that. That's just the integral. Well, let's use calculus for fun. Okay. Yes, I know we could do the whole base 10 type thing. But yeah. Yes, we can do that. So I'm going to integrate, say, from 0 to 7 of negative 5/7 x plus 5. So that's important because this area also gives me my mass, m, if rho is 1. Right? Other things I need to calculate are the moment about the x-axis and the moment about the y-axis. So let's write those out, and then we'll calculate all 3 integrals. Switch colors here. So the moment about the x-axis is the integral from 0 to 7. Now my rho is 1. If I'm going about the x-axis, I need the distance vertically away from x, so that's a y value. So that one right there was my function squared. So negative 5/7 x plus 5 squared. There was a slight catch in there. What was the catch on the constant?
It was half.
1/2. Yeah. And then I need the moment about the y-axis. So if I'm going to go about the y-axis, the distance away from the y-axis is an x value. So that one gave me the integral from 0 to 7 of x times my function. So we need antiderivatives for each of these.
It's not square at the bottom, is it?
No, it's
Oh shit, that's not supposed to be squared. No. It's x times the y value. That's x times the function. Yep, so we need each of those integrals. Evaluate. So find an antiderivative. On the black and the red one, algebra first, antiderivative second. Go for it. And a glass of water, I'll be right back. Those- X.
What is the term of this?
The integrated.
Oh, I didn't integrate yet. Thank you, I'm ahead of myself. What's that?
49 times 3 is 147.
Oh, I'd rather not multiply that. Thank you. Is this 175/6? Anyone get that?
Yeah.
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 Sure.
Keyboard.
All right, so 35/2, 175/6, one more to do. So then we can identify our center. So what do we want next? We have my. What do we get here? Factor out 5 times 29. That leaves 1/3 plus 1/2. 1/6.
245.
Okay, so now that we have those three numbers, you guys might catch up, we got to do the appropriate divisions to end up with the center for each of these. Center X, center Y. Let's see. Again.
175/6.
175 is what? 25 times 7? All right, so then center X value comes from the moment about the y-axis, because that involves x's. So that's going to be that 5 times 49/6 divided by the mass, which means multiplied by the reciprocal. And then stuff cancels quite wonderfully. 2 goes into 6 3 times, and 5 goes into 35/7, and 7 goes into 49/7. So I get 7/3 for the moment about the x-axis. The moment about the, sorry, not the moment, the center y value is going to be 25 times 7, 6 times 2 or 35. And again, a whole bunch of stuff cancels.
I have a question.
Yeah.
What's the formula for the x with that n over it?
X bar, that's the average x value. That is the moment, oops, the moment about the y divided by the mass. And similarly, this y is moment about the x divided by the mass. Okay. 7/3 center X, 5/3 center Y. Redraw that picture. Switch to the other pen so I can be neater. So let's see. 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5, 6, 7. So here's my triangle. Make believe that's triangle. So much for being neater. So let's see. Center x value is what? 1/3 of 7, 7/3, which
Yeah.
is 2 1/3. So right, let's switch colors. Right about here is 1/3 of 7, 7/3. And the center y value is what?
5/3.
5/3, which was 1/3 of 5. So that would be what, 1 2/3? Be right about here. So the center of mass is about right there-ish. Seem reasonable?
Yeah.
Okay. Now notice it's not halfway in between 0 and 7, and it's not halfway in between 0 and 5. If you orient the right triangle this way, from the right angle, it's going to be 1/3 of the way in each direction, it turns out. So if we put different numbers in here for the height and the width of this right triangle, we would find that the center x is 1/3 of the way over from the right angle, and the center y is 1/3 of the way up from the right angle, which is kind of cool.
That's a rule of thumb.
That is a rule of thumb, yeah. So if we redid this again and we said like this is B and this is A, then we would find that the x bar would be 1/3 of A, and y bar would be 1/3 of B.
We can use that on the test.
No, I want to see the integrals. And I'll give you a more interesting shape. Yeah, now there's going to be some shapes where this is going to be hard to calculate. Go back to our formulas over here. Like, for example, if this was, f of x was the sine of x, x times the sine, we played with that before. Do we have an antiderivative for that?
No.
No, we don't. Does one exist? Actually, it does. We'll learn how to find that in a couple of weeks.
Oh, so there is one.
The sine squared. I haven't done that one yet. Maybe with trig identities we could do that. Otherwise, we need some other technique to do it. Yeah. So sometimes this can be a problem, just like sometimes when we found volumes, the integrals were pretty tricky and we had to resort to technology, which is all right. All right, next thing we're going to do is we're going to apply the formula of the theorem of Pappus to this. And the theorem of Pappus says,
You passed.
I know, I'm going to restate it. The theorem of Pappus says that if you're revolving about an axis, so let's say we're going to revolve this about the y-axis, then what you need to know is you need to know the center value. We've got a center point. And you need to know the area. Oops, that was supposed to be a highlighter. You need to know the area. Okay, so let's see. What do we know here? Do we know this area here? We do. We already found it. In calculating those centers, we had to know the area. So we know that area. We calculated that area to be, so that's the integral of f of x dx, 35/2. All right. And then if we're going to revolve this, we need to know the distance from the center of this object to the axis of rotation. Do we know the distance from the center to the axis?
We do.
Yes.
Yeah, that's right there. Okay. When I revolve this, what kind of shape am I going to get?
Like
Pyramid.
pyramid thing.
Cone.
Like
A cone. Yeah, I'm going to get a cone out of this. The radius of that cone is r equals 7 at the base, and the height of this cone is 5. We'll apply a cone formula to a minute, but let's apply Pappus's theorem. Pappus's theorem said the volume is going to be equal to the area of the cross-section you're revolving times the length of the path the center moves through. Okay, my center is going to move through a circle, right? Because I'm revolving around an axis. So that means the path is just going to be 2 pi times that radius, and that radius happens to be 7/3. The area of this triangle we discovered was 35/2. So according to Pappus, that should be the volume of this sucker. Area of the cross section times the path the center makes around the axis or something. All right, so cleaning this up just a little bit. It doesn't clean up a hell of a lot, but it cleans up a little. The 2's divide out. That's about it. That's about it. So we end up, and 35, by the way, is 5 times 7, right?
Mm-hmm.
So like if I break down the factors here, there's a pi hanging out, there's a 5, there's a 7, and there's another 7, and then I'm going to divide by 3, whatever that ends up being. That's the stuff that's left. Okay, so yeah, pi times 5 times 7 squared over 3, whatever that ends up being. Now, does anybody remember the formula for the area of a cone back from the geometry days or earlier this class?
1/3 base times height.
1/3 area of the base times the height. Okay, the base is a circle. How do you find the area of a circle?
2 pi r squared.
2 pi r squared. So well, we're mixing
2 pi.
circumference and area.
Shoot.
It's just pi r squared.
Pi, yeah, 2 pi.
Okay, so we're going to get 1/3. We're going to get a pi times the radius, 7 squared, times the height. Does Pappus's theorem match what?
Yes.
Yes, okay. And we could have done disks or shells to do this if we were really cool. And we would get the same number from disks or shells. And that was exciting. And we're out of time. Perfect. All right, so we are officially a day behind. What does that mean? Let's see. I have what to cover still. We have integrals of exponentials and logarithms. We've pretty much already done that. What's the antiderivative of e to the x? What's the antiderivative of 1 over x? ln x. Yeah, that's all that's in 2.7.
Oh, great.
That's going to be a pleasant break. Exponential growth and decay are applications of calculus with exponential functions. And then hyperbolic functions, now that's going to be a little kick in the pants.
Right for the test.
So most likely the test will not be a week from today. It will be the beginning of the week after.
Oh, ew.
We're a day behind.
Okay.
We're a day behind.
A test on a Tuesday?
Yeah, looks like that's what's going to happen.
Oh, that's gonna suck.
It's okay with me.
A test on a